So we have some children playing on a roundabout. How wonderful. I hope it's the kind not for cars and it's the one on the playground. So we have a few kids and Riley pushes the roundabout and gets it spinning. So I assume he sort of runs along the side, gives it a big push, and now this spinning platform is spinning at a constant angular speed. Now we're told it makes one revolution in 1.23 seconds, and we're asked to show that the angular velocity is about 5.11 radians per second. So let's just have a think. Angular velocity, there are a few equations you might be thinking of. So at its sort of most basic definition, it's the change in angle, angular displacement over the time. Do we have an angle? Kind of. We're given the time for one full revolution, and in a circle, one full revolution is exactly 2 pi radians. So you might have actually seen this equation before, 2 pi over time period, and that's exactly the angular displacement over the time, but for one full revolution. So substituting in, what is that, 1.23 in for time. Let's double check on our calculator. 2 times pi divided by 1.23 is 5.10828 ... which rounded to 3 sig fig is 5.11 radians per second. Awesome. You might have also seen in your formula book V equals omega times the radius. This is the equation that relates the tangential, or like the linear velocity, to the angular velocity. And in this problem, we didn't use that because we had no information about the linear velocity, or the radius, in fact. All right, part B. Okay, after Riley gets a bit tired, he stops pushing, and 30 seconds later, the roundabout has slowed so that it takes 2.04 seconds to make one revolution. So notice that's a greater time period, right? So it has indeed slowed down. It can be approximated by a spinning disk with a rotational inertia of 57.6 kilogram meters squared. Two parts: determine the average angular deceleration, and then calculate the average frictional torque. So let's label what we have in the question. So Riley stops pushing. 30 seconds later, it has slowed. Okay, so that is a time between its initial angular velocity that we worked out in the previous question, 5.11. Right, so it started off at 5.11 radians per second. After 30 seconds, it now only takes 2.04 seconds to make a revolution. And just like in part A, we can work out what that angular velocity is. So 2 pi divided by 2.04. 2 pi divided by 2.04 is 3.08. Oh, off the screen, but radians per second. Right. One revolution is 2 pi radians in 2.04 seconds, so an angular velocity of 3.08 radians per second. So we can clearly see the final velocity is less than the initial. That's because it has decelerated. And the symbol for angular acceleration is alpha. And so that's what we are looking for. We know the time, the initial, and the final angular velocity. So what equation relates that together? Well, we could use angular velocity is the change in velocity. Excuse me, angular acceleration is the change in angular velocity divided by the change in time. Right, it's very similar, if you recall, to linear acceleration. And so substituting in what we know, final angular velocity, 3.08, take away initial, 5.11, all divided by 30 seconds, which gives negative 0.0677, and then units, what's angular acceleration? So it's radians per second squared. And notice the negative, that just indicates deceleration. Right, because the final is less than the initial. Great, so that will be achieved, finding out the angular acceleration. And now the second part, calculate the average frictional torque. So in order to accelerate or have an angular deceleration, there needs to be a net torque opposing the motion. And in this case, it comes from the friction, like the friction of the bearings or air resistance, for example. And just like Newton's second law for linear motion, F net equals mass times acceleration, we have an equivalent expression, but for rotational motion, where the net torque is equal to the rotational inertia, which relates to the mass, but also how far away from the rotational point it is, times the angular acceleration. And so we just worked out angular acceleration, and we are given the rotational inertia. So we can solve for the net torque. So substituting that in, 57.6 kilogram meter squared times negative 0.0677 radians per second squared gives negative 3.89 Newton meters. Notice I rounded to 3 significant figures because everything else was to 3 significant figures, so we can't be more precise than that. And this is equal to the frictional torque. So just explaining that one more time, what we worked out was the net torque, and the only force acting on this roundabout is friction. Right? Riley has stopped pushing, so there's no more applied force. The only force slowing it down is friction, which means the net force is equal to the frictional force. And since we worked out the angular acceleration, we were given rotational inertia, we could work out the net torque. And so that would be a merit question. Part C. Oh, look at that. They got friends. How nice. Riding on a roundabout. Green and blue are a little bit close together, and then light blue and orange are a little bit further apart. So they're not symmetrical, but that's all right. And they're spinning clockwise. Explain, using physics principles, what the friends can do to make the roundabout speed up while staying on the platform. Okay, exclude all influences external to the platform. Okay, so we can't say Riley gives them a bigger push, as that's an external influence. We can only move their positions around. I don't know if they could lose weight instantly. Maybe if they had a bag, they could throw it off. So they're wanting to make this go faster. Awesome. So I strongly recommend, if you're sitting in an office chair right now, you can do this. Right, you spin around with your arms extended, and then as you start spinning, you bring your arms close to your body, and what you'll find is you spin faster, right? Just like a ballerina or a figure skater. And we can apply that exact same scenario, but to these students going on the roundabout. So if they all moved in, just like you bringing in your arms, their angular velocity would increase. And now we need to explain that using physics principles. So let's write a few bullet points. So our first point could be the friends could move towards the center. Great. So that's what they could do. Now let's try to explain that. So what happens when they move towards the center? Are they changing the mass? Not quite, but they all do have mass. And so what they're changing is their distance from the axis of rotation. That's what they're changing. So we could say reducing their distance from the axis of rotation. Right, that's just the center of the circle, assuming it's like uniform. And so what does that do? Well, related to their mass is the rotational inertia. So if they come closer to the axis of rotation, they're reducing the rotational inertia of the system. Okay, and now how does that link to them going faster? So, conservation of angular momentum. Angular momentum equals rotational inertia times angular velocity. So since there's no external forces, there's no friction or anything, right? It says to exclude that. We could say there will be conservation of angular momentum, which is the symbol L. And if their inertia is reduced, so their inertia is reduced, their angular momentum, we just said, is conserved, so that's not changing. Their angular velocity must therefore increase in order for their angular momentum to stay the same. And those 4 points would be excellence. Or 5 points. These ones right here. Right, reduce the distance from the axis of rotation. In other words, if you're on your office chair, you pull your arms in. What does that do? It reduces the rotational inertia. You may have seen this formula before. Inertia depends on mass and radius. So they're not changing their mass, but they are changing their radius. And by conservation of angular momentum, which we can assume if rotational inertia decreases, angular velocity increases. Right, so they will speed up on the platform. And final question, Matilda wants to run and jump onto the initially stationary roundabout. Okay, so slightly separate scenario, and holding on to poles A or B. She wants it to spin as fast as possible. Okay, so thinking about that, where would you jump? I would probably jump at A, because it looks like the component of the jump is more perpendicular, so it'll want to rotate more, whereas this one is less so. So Part 1, assuming that she always jumps at the same speed, explain which jump will make the roundabout go faster. So to help, we can consider, instead of making it confusing and being like Matilda's jump, we could just model the moment she lands on the roundabout as a force. And so assuming she has the same speed, the same momentum, she stops in the same time, if she jumps at A or B, her force exerted on the platform would be the same. Right? The only difference is the position that she exerts that force upon. So the axis of rotation is assuming in the center of the circle. I'll just draw a few radii. So looking at position B, we could split that force vector into a component going that way and a component going that way. And notice that part of the force is actually acting inwards to the center, and that wouldn't cause it to rotate. It's only the perpendicular component that causes it to rotate. So at position A, all of that force is perpendicular, which means position A would definitely produce the greater speed. So let's put that into some bullet points. So we could say, so force is the same at A or B, right? Because she has the same speed, the same mass, assuming the collision lasts the same time, by impulse, the force exerted is the same. What else is the same is the radius is the same, right? Notice they're both at the edge of the circle. So what's different? The difference is force at A is perpendicular to the radius, like at that point, whereas at B, is, we could say, partly perpendicular, right? Part of it is perpendicular, but part of it is not. And so what does this mean? Well, this means that the torque at A is greater than the torque at B. Right, recall that torque is force times the radius or distance, where F is perpendicular to that distance. And since A is fully perpendicular, B is only partly, the torque at A is greater, resulting in the greatest speed. Cool, so just to recap this one, key points are A and B. At positions A and B, they are the same distance from the center. The force exerted at those points is the same. The only difference is the component that is perpendicular. And since at A it is fully perpendicular, it'll create a greater torque, resulting in a greater speed. You could also talk about angular momentum by a similar argument. All right, finally, part 2. She subsequently lets go and slips off. Discuss the possible effects on the speed of the roundabout. Okay, so we don't care about Matilda, that's fine. Speed of the roundabout. There is negligible friction. Okay, so that means as she slips off, she's not like kicking back to slow down the roundabout through a force. So we're ignoring that contact friction. So is it going to speed up or slow down? So what's changing is the inertia. I initially thought since she slips off and she has a significant point mass, that the inertia would decrease, and by the previous question, if inertia decreases, angular velocity could increase. Right, that's where I started. But looking into it a bit more, what is happening is we need to consider the roundabout and Matilda, right, as a whole system, so combined. And when Matilda slips off, true, some angular momentum is lost, but that's only her angular momentum, and that is then going into her linear momentum. Right, so there's that connection between, if you'll recall, mvr. Angular momentum is linear momentum times the radius. And so even though the angular momentum of Matilda has decreased, it has gone into her linear momentum. So the speed of the roundabout would remain constant. So let's try to put that into a few bullet points to clear it up. All right, let's start with, actually, I just thought of a better way of explaining this. So let's go back a few steps. Delete. All right, take two. So when Matilda slips off, we can assume there is negligible friction. So what that means is, as she slips off, she is not kicking back at all. So there is no net torque applied to the roundabout. And if the net torque is zero, right, because we're ignoring friction, we know net torque is equal to rotational inertia times angular acceleration. And since net torque is zero, angular acceleration must be zero, therefore no change in angular velocity. So as a sentence, we could say Matilda does not exert a torque, right, or a force at some distance, at some radius. So Matilda does not exert a torque. So net torque is zero. So angular acceleration is zero. So no change in angular velocity, right? Or the speed on the roundabout. Whew. All right, and that part two combined with part one would be another excellence question. Go us.